So before we take a look at why Wegner thought the continents moved, let's learn a little bit about Wegner himself. Wegner was a meteorologist and a polar explorer. He was actually a person that went down and explored Antarctica in the very early 1900s and late 1800s. What's actually pretty interesting about his life is that's actually how he died. He went on a polar expedition down in the Antarctic and was never seen from again. So he was definitely a very eccentric man for his time. But he wrote a book called The Origins of the Oceans and Continents in 1915, and in this book he suggested that the land masses slowly moved. Now what's important to recognize about this is Wegner didn't think that the oceans moved, he just thought that the continents moved, and that's what we call continental drift. Okay? So like I said, he thought that the continents moved, and he thought that they kind of plowed through the ocean. The way I like to envision it is if you've ever watched any of those ice shows on the Discovery Channel where they go fishing and stuff, you might have an ice field and this big boat kind of goes through and plows it open. That's pretty much how Wegner thought the continents moved, right through the ocean floor. He also was the person, like I said, that came up with the idea of Pangaea. So he thought Pangaea, right, was composed of two supercontinents, Laurasia, which is North America, Greenland, Europe, and Asia, and Gondwanaland, which was the rest. And he thought that at some point in time, these two major supercontinents had come together to form a large supercontinent. And he thought that may have happened about 250 million years ago. So let's look at Wegner's evidence, right? What did he see that led him to this idea of plate tectonics? Of continental drift and of Pangaea. Well, there's 5 lines of evidence. Okay, he looked at the fit of the continents, glacial deposits, paleoclimate belts, which that just means old climate, fossil locations, and matching geology. So let's take a look at each one of these lines of evidence. So the first one is continental fit. Wegner noticed when he looked at a map that these continents look like they fit together, kind of like the pieces of a puzzle. So if you take a look right over here at this diagram, you notice, especially between South America and Africa, that they look pretty good, right? They look like they match up pretty well. You can also see that nice fit between Greenland and North America and Africa, right? Everything seems to match pretty well. He actually cut out pieces of a map and placed them together like pieces of a puzzle. Now, the problem is that the shorelines, however, don't exactly fit. But if you think about this for a second, right, you can easily explain that. What happens to the shoreline on a daily basis? Well, the answer should be it erodes, right? We know all about that living in coastal Louisiana. So what's actually interesting is the shorelines would never ever match up. But today, right, we have the ability, with using satellites, to see what the continents look like underneath the water. And what's pretty cool is if we actually were to drain out all of the water in the ocean, we would see that these continents actually fit together perfectly. So that's pretty great. Now, of course, he didn't know that, right, in 1915, but we now know that today. So we can explain why the continents don't fit together exactly, right, at the shoreline. He also took a look at glacial evidence. So what's pretty interesting is if you look at where glaciers have been about 250 million years ago, if we look at this map on the left, right, everywhere that's outlined in white has evidence for glaciers. And what's even more interesting is when you look at evidence for glaciers, okay, a glacier moving on a rock, glaciers kind of act like sandpaper as they move over the rock. So they leave these little grooves, okay, in the rock. And those grooves actually then tell you the direction, right, that the glacier is moving. So imagine having some sandpaper on wood, right, and rubbing it back and forth. You would start to make grooves on it. Okay, those are what we call the striations. Same thing as a glacier. So you would know which direction you were rubbing that sandpaper, right, by looking at those striations. Well, if we look at the distribution of glacial evidence from 250 million years ago today, the glaciers seem pretty random, right? You see some on South America, some on Southern Africa, India, Australia. If we thought the continents didn't move, it would be very hard to explain the presence of all of these glaciers. Right? We know that ocean water can't freeze because it's too salty. So it would be very difficult to explain how these glaciers grew from the South Pole right onto these locations. Now, what's even more interesting, what Wegner did is he put these continents together. He fit them together like pieces of a puzzle. And when you do that, you notice this glacier starts to line up. Right? And what's even more interesting is you can see where the center point is, and all of those striations radiate out from that center point. So that's some pretty strong evidence as well. Then he looked at paleoclimate, which is similar to that glacial evidence. He looked at the rocks, and we're going to learn how to do this in a couple of chapters. And certain rocks tell us about the environment. For example, right, if I find a sandstone, well, I know that either formed, right, at a desert or at a beach, right? So certain rocks can tell us about different environments. So what he did is he took those rocks, right, and mapped out those environments, as you can see here in the legend, right? We have swamps, and right, we have swamps here in green, we have deserts, and he mapped those out on the continents, then put the continents together as he thought Pangaea was, and lo and behold, all of these climates match up across all of these continents. Right? So that's pretty cool. He also looked at fossil evidence, which to me is the best part because they're fossils. So he looked on these different continents you can see here, and he noticed different fossils like Mesosaurus, which is a swimming reptile, Lystrosaurus, right, which is a mammal-like, an early mammal-like reptile, Glosterus, which is a fossil fern, and Signathus, right, which is also a mammal-like reptile. And he plotted out where we find those. And what's pretty interesting is you notice we don't find them just on one continent, we find them across most of these continents. So Mesosaurus we find on South America and Africa. Well, this is a small swimming reptile. Today, South America and Africa are separated, or excuse me, mostly we find those in freshwater, but today South America and Africa are separated by thousands of miles of ocean. Right? What are the odds that this small reptile could swim across a huge ocean? Well, definitely couldn't. Especially when we start looking at things like Lystrosaurus, right, which we find on India, Africa, and Antarctica, and Signathus, which is on South America and Africa. These are land-dwelling reptiles and mammal-like reptiles. We do not find them. They are not ocean-dwelling creatures, so they would not be able to cross the ocean. But if we place the continents together, you can easily see how they could walk, right, from one continent to another. So that explains their distribution. And finally, we can look at matching geologic units, meaning we can look at mountains. Right? We're going to learn in this chapter that when two continents collide, that's when they make mountains. They buckle, just like if you had two cars coming together on a head-on collision, right? Their hoods buckle. Continents do the same thing. So what's interesting in South America, on the eastern half of South America, we see these mountains outlined here in green and then the squiggly brown line. These are two different mountainous units. If we look at the western part of Africa, we see these same mountainous regions. Now, what's even cooler in my book is when you put these continents together, they match up, right? You can see how this green goes from Africa into South America, right? And these lines match up pretty much seamlessly. So that definitely goes to show us that these continents were together. We can look at our own continent, and we see the same thing from North America and Africa, right? When the eastern part of North America was connected to the western part of Africa. We have these matching mountain belts. So Wegner's evidence, to me, seems pretty airtight. However, there was a lot of people that criticized these ideas. And basically, a lot of the reason is we didn't have the technology to understand it, right? Think about the early 1900s. We didn't have satellites. We didn't have computers. It was very hard to understand this. For a basic example, right? Sitting there at your home listening to this lecture, can you feel the Earth rotating? No, right? So how do we know that the Earth is moving, right? So today, of course, we can monitor those things by satellite, but back before that technology was there, right, well, it's kind of hard to make the case for it because we can't feel it. Now, the biggest criticism of Wegner's was what would cause the plates to move. Wegner did not know the answer to that. He thought that the spin of the Earth was making those planets, or was making the plates move, right? Centrifugal force. We now know that's definitely not why the plates are moving. The Earth would actually have to spin so fast that we would actually be spun off into outer space, right, in order to get those plates to move. However, what we're going to see, right, is in the 1940s, 1950s, we started getting new evidence from the ocean. And once we started getting these lines of evidence from the ocean, people started revisiting Wegner's idea, realizing, maybe he actually wasn't crazy. Maybe there was something to his ideas.